and you would be starting doing it, because I want that you utilize this time, and also if you have doubt, you get it clarified and here discuss with us. And in the meantime, the TAs would be asking you and call you and ask you to explain whatever you have done, and just have some assessment. So this one also, the second problem, this third problem, we will be giving 2 working days for doing the design and the simulation here. So this one is, just a minute. Mm, just 1 minute. Where is it? Yeah. So can you see it? Yes.
Yes, sir.
Okay. So sorry. This is a design of a flow meter, because flow meter is, we have already discussed in your third, that flow meter is a very important area, uh, instrument, and mostly for measurement or some liquid flow measurements we use it. And there are mainly 2 types of flow meter: orifice and venturi type flow meters. So if we recall that the orifice or venturi type flow meter, both of them provide an obstruction to the flow path, and obviously we assume that the flow rate is, I mean, the Reynolds number is more than 4,000 or 10,000, so that it is a turbulent flow. And due to this obstruction, what will happen before the and after the obstruction, there would be some pressure difference would be created. And this pressure difference, we measure it using a pressure. Uh, okay, using a pressure sensor, and then again you need to have some signal conditioning circuit, and also uh, the final area. So in this case also, our A is that we have got 4 groups. So the design problem is for 4 batches. That is a 1400 0 to 1400 kg meter cube per hour is the input flow rate. Group B, it would be 0 to 1600. Group C, 0 to 1800, and Group D, it would be 0 to 2000 meter cube per hour. And you have an option, you can choose, because ultimately it is the A there. The flow meter, you can choose either an orifice or a venturi type. We know the orifice meter is easy to construct, but it has got certain, and cost is low, but it has got a permanent one, while the Venturi is a construction is difficult, but and the cost is more, but its permanent pressure drop is almost zero. Yeah, 1% or 2 correction, and it is the water, the liquid is flowing through a pipe of the liquid, so 1000 kg per meter cube is the density. Its viscosity is SIU. So that uh, so that you can have it, you can find out the Reynolds number rho Vd by nu. V is the velocity you can find out from the full scale range and like this. And if the Reynolds number is more than 10,000 or like this, you are satisfied that our assumptions or that the design is correct like this. And the output voltage is 0 to 2.5 volt DC. Now what will be, oh, I think somehow, where is it? Oh, I think somehow, okay, I'll just put it like this there. Okay, I think it's not coming somehow. Forget it sometime. Okay, so what we have is that several, so basically, as I told, it's an instrumentation or a system or a measurement system. It consists of several. So input is flow rate, and we have the first one is the orifice and or the venturi, whatever you choose, that is your area. I suggest that you choose randomly your area. So the output of it is delta P, and the is delta P obtained. And what we do is that for delta P, you can use the pressure difference to electrical signal. You can use a diaphragm type pressure gauge. Actually, this, I mean, diaphragm type pressure gauge are like this. They are diaphragm type pressure gauge, and we know once so that if the pressure, I mean the flow rate changes, the pressure difference will change, and we can measure the, and that will cause you some the displacement, that will cause you some displacement of the diaphragm. Or so we can measure the displacement of the diaphragm by using a strain gauge rosettes, which we have already discussed. Or for the sake of simplicity or the idea, let us do it for this case using a capacitive sensor. Diaphragm type capacitive sensors again we'll have to design, and so it is a, always it is better to have a differential capacitor or like this. Uh, so we'll have to design the of the delta C. So delta P will be converted into the corresponding change in the capacitance. It is always better to have a differential capacitor because the sensitivity will be higher and etc. But you can, if you want, you can use a one fixed capacitor here. So finally, though this is a delta C is the output here, and so we need to have some circuits or signal conditioning circuit for measurement of delta C. So definitely capacitive sensors. We have different types of capacitive sensors we have seen. It could be footage, different capacitance amplifier, or several things. And what we require is that that will be an AC voltage. Definitely the capacitance sensor. We are mostly the best way is that the AC voltage, but if you want, you can employ some DC with the proper arrangement and also. So I am saying that say suppose we are using some AC voltage there. So and then we require some amplification, and after the amplifications, we require a phase sensitive detector, a PH, for demodulation and a low pass filter, so that the direction of flow rate is uniform and it can be detected, and also ultimately the output of the signal conditioning circuit is a some DC voltage. But again, so this is a typical, I have given that a guideline. So desired capacitance, that means C0, you just say that you design the diaphragms and the gap is such that the C0 is the nominal capacitance is around 10 picofarad. And you just look for it that delta C by C, that is a percentage change in capacitance, is around 5%. And if we require, this is the formula, delta C by C for a capacitance type diaphragm is that P into 1 minus mu square. Mu is the what is Poisson's ratio, r to the power 4, 16 ET cube into D, like this there. So this is the thing. From this one, we have to assume what is their gap, what is the there, all the things we just get it like that. So we get some DC voltage. But that is not enough, because we know that the flow rate is proportional to the square root of the pressure difference. So what we are getting is that the output voltage may be the square proportional to the delta P, that is the proportional to the pressure difference. So we require a square rooting circuit to get a square root of this one, so that ultimately the output will be 0 to 2.5 volt DC, and by using the square rooting scheme, we'll get a complete linear arrangement. So this is our target, but definitely there would be some non-linearity at different places. Our overall non-linearity should be less than 5%. So multiple tasks are involved. One is the design of the orifice, that what would be the orifice dimensions, and what you need is that at least to draw it, if not, if possible, by hand itself, by sketch itself. But the orifice or venturi has got certain standard design dimensions there. How would be what would be if it is an orifice, what should be the shape of the orifice plate, what is the angle, and if it is, what is the if it is a venturi, what should be the converging angle, what should be the diverging angle. These things are partly available in Bentley, and many other A's are there. So definitely, as I told, that whenever I design the orifice, so I will also look into that one, that what would be the dimensions and etc. And from that one, I will have to calculate what is the value of the discharge coefficient. Similarly, for the diaphragm, what we need is that basically in the pipeline there would be a pressure drop, and this we should take some tapping from both the sides, and you need to put it in a diaphragm. But if we are using a capacitive sensor, diaphragm provides a fixed rather moving plate. There must be at least 1 or 2 fixed plates nearby, so that the capacitance variations or differential capacitance variations can be measured. So naturally, we can use several techniques. One is that you use some, in that path, you use some sort of perforated type of fixed capacitors, so that the pressure difference is transmitted but the capacitance remains. I mean, we can have a fixed capacitance like this here. So the design of the diaphragm, capacitive sensors, again the supply voltage, what voltage we should give, frequency, and all the what excitation I should give it, like this here. So what is there? It is a guideline. It is given the desired full scale delta P is 10 to the power 6 Pascal. Desired delta C0 is equal to 10. I mean, nominal value is 10 picofarad, and full scale delta C by C is 5%. And after that one, what we require is the delta C I am getting, but the signal conditioning circuit. That means how to employ, whether it is a bridge or a capacitance amplifier, and their modulations and the low pass filter, all the things have to be done so that delta V is around delta V, that is a DC voltage we obtain it. And we must so design of the sensing scheme, amplifier, first sensitive detector, low pass filter, these are the tasks here. And last, we need to have a square routing circuit. We have discussed that analog multiplier circuits here, and these analog multipliers could be used by analog multipliers could be a circuit, and that will be give you the square routing voltage. Finally, our outcome should be whatever for the full scale flow rate, it should be 2.5 volt DC, and it should be linear within this 5% accuracy. So you can see that this one involves a more number of components and circuit parts like this there. And we have got a design of the mechanical design as well as the electronics and other circuit. That means we'll have to design the venturi, orifice, as well as the diaphragm. That we'll have to. So diaphragm can this, or if you want, you can use some sort of polymer. You coat some metallic coating on like this, but you can use a stainless steel. That would be easier for you doing that one. So all the things, and always you try to, you will have to design, and naturally you will have to design one by one block after, by each block will have to individually. It also says that you make some sort of budget. That means in this case, that is a orifice, the design of the orifice or venturi is that flow rate is given that one, and the delta P should be around 10 to the power 6 pascals. Similarly, the C0 is this one, and it is around 5%. And similarly, for each block, the whatever may be, what is the input variation and what is the output variation? Just try to have a budget there, and finally, an adjustment of this one there. It is always better to use some sort of potentiometer where you can adjust the sensitivity at the final level or like there, get it in the desired input or output range there. So we'll have to start this one, and definitely the Bentley's book or any measurement books and etc. would be there useful. And also, as I told, that if you are using an analog multiplier, what analog multiplier you are using, what is their circuit configuration, you have to look into their data sheet and connect it and give it like this. So this will also, I will give you 2 working days time so that you can complete. And if you have any questions or doubt, you can ask me. I'm sorry. Question? First thing is that you will have to recapitulate whatever you have done or studied earlier in the instrumentation devices one, or take a book, you or use a class note to recapitulate all the things there. And possibly you remember those things here there. So what would be the scheme, each scheme, please try to find out and do that things there. So these things are individually you have done some part of the design, but complete design is an exercise there. So any question?
Sir, how do we simulate venturi or orifice?
No, you cannot simulate here.
So then,
There are ways for simulations and etc. So the point is that you may simulate, and similarly the diaphragm also. You cannot simulate. These things you can use some formulae. You see, you use those verb venturi formulae you will have to use and say like this, but you may simulate the signal conditioning circuit or square rooting circuit. So what we can say, if the flow rate is varying between this 0 to 1600 like this, what would be the delta C variation and what is C0 and like this there. And for that one, the signal conditioning circuit, you may try to get what is the simulate this one and the square rooting circuit. But the mechanical part is that in the same way, it is difficult to simulate. Okay.
So is the design just limited to theoretical design?
But every design is a theoretical now.
No, I mean the design is just limited to us deciding the parameters. We don't have to simulate it or verify it.
What I would say that simulate the signal conditioning circuit as well as the square rooting circuit.
Yes.
But this time, these two parts you cannot really simulate. It's the problem. We don't have much of their tools to design the mechanical as well as the electrical both together. So that is a problem. But here we have some formulae, and based on which you try to design those things. Okay. And this simulation should be after you complete the design. Ultimately, the design will be based on your hand calculations and like this there. The simulation is only okay to see that okay, it works fine, the complete system works fine. Okay. Any other doubt? Yes? Anybody?
sir, in the previous experiment
Yeah.
number 2, so you said that output should be between 4 milliampere to 20 milliampere. So we need to have any range in that, or the minimum should be 4 and maximum should be 20 or
Yeah,
less?
minimum should be 4, maximum should be 20.
Okay.
But here it is not that part we have left it. It is only 0 to 2.5 volt DC for the sake of simplicity. Okay.
Sir, for that part, like minimum should be 4 and maximum should be 20. So for that part, it is getting very difficult. Like I am not finding any particular way to simulate that.
No, simulation will not be able to do it. That XTR 100, I told it.
Yes, sir.
Its tool is not available. And apart from XTR 100, also you can, using discrete components or the other ICs, also you can design it. So leave that part. But the other design you can complete. Okay,
yes,
microcontroller and etc.
Sir, can we eliminate the memory storage part, because like both things in a single simulation software is like next to impossible, sir.
No. Simulation, you see, I always tell that you need not show us all the simulations, all the possibilities. Simulation is only a tool to help you. that we have done it like this. The first important thing is that how to store the memory and etc. This arrangement and the program will have to do it. And partly you can, whatever is possible, I also do not know completely. Whatever is possible, you should show the simulation. That will give you the confidence. Okay, it will work. Okay.
Okay, sir.
Any other questions?
Hello, sir.
Yes.
Sir, I have done like the whole signal conditioning circuit for the previous experiment in LT Spice, and actually my range is from 100 degrees Celsius to 200 degrees Celsius. So whenever I'm like sweeping the temperature from 100 to 200 in steps of 5, it is able to converge the results in all the places. But let's say I'm taking a temperature of some random like 167, then it is not able to converge the simulation. For some reason, I'm not able to.
Naturally, you will see every simulation software has got certain limitations, as well as the memory space limitations and where to start. Actually, it's like this a solution of a differential equation. What is the initial guess and what is the increment? These are all involved. So naturally, you cannot get there. But if you are getting it within steps of 5 degrees Celsius, working is fine. There is no issue.
Okay, thanks.
Any other issue?
Yes, sir. One more thing regarding the previous experiment.
Not experiment, it's a design.
Yes,
Okay.
So basically, I am simulating that in Tina TI. So while I am using some practical op-amps for amplification parts, so at that time, when I'm doing a temperature sweep from 100 to 200 degrees Celsius, up to 195 degrees Celsius, the output is coming linear. But after 195 degrees Celsius, there is a sudden drop in the output. Basically, I guess that it should be due to op-amp breakdown or the practical nature of op-amp.
Op-amp breakdown. Why op-amp should break down?
So because of
what is the output?
like, the op-amp datasheet I read, which
op-amp datasheet you have read it, but are you keeping the op-amp in that temperature?
Like in Tina TI, I guess it is implementing that temperature sweep on whole circuit, on the complete circuit.
That is a different story there. I don't know because I am not familiar with all these things here. But what I wanted to tell at this juncture is that these designs are also very different depending upon its use. There are certain military grade designs and like this, and even the op-amps and etc. They are to pass through different condition and the temperature variations and like this, because if it is in war field or like this. But most of our design, we assume that these equipment are kept in room temperature. It's not varying much, 300 or like this. And whatever be the sweep you are telling, so if you give it at so high, then it is may drop, I do not know. But what you can do is that you know the RTD or thermistor, so or RTD or thermo or whatever, I don't know what type of temperature sensor did you use?
Sir, RTD.
RTD. So what is the value of resistance changing? If you sweep that resistance variation, can you not do that?
Yes, sir, that would be possible.
No, so do that one. So it is it is always giving you some helping hand, this simulation, to give you confidence. But it cannot really mimic the actual situation, because you know that will be that simulation because they are improving, the simulation platforms are improving, because it would be too much to expect. And often we require, some of them have got a specialized software for particular design or particular simulations. We don't have those things. Any other issue or any other question?
Sir, one general.
Sir?
One by one. Yukta?
Yes, sir. Sir, I had designed the thermometer using Atmega 32 microcontroller, ADC, and thermocouple. But sir, for some reasons, I'm not able to interface that circuit to a LCD. I'm like facing a lot of problem with it. I even checked the data sheet of LCD, but I'm still not able to do it. So sir, would it be fine if I just remove the
No. Yeah, that's right. I would say that this is your experience. That is, I don't expect you will be able to complete everything and everything is working fine. You just say up to this I could do it, but this part I made it, but it did not work. But anyway, you may discuss with your friends, try to see. Maybe you have done some silly mistake also. Check it. Don't be frustrated or like this. Don't expect that I would give you that you need
No,
to
sir,
give
I'm
me a
not saying
complete.
it. I'm not saying it. Sir, I have the fact that I am not able to add an LCD interface to it. So, would it be fine if I just use like a normal print statement and it like prints the temperature on terminal or something? Will that be acceptable?
Okay, whatever you could do it, let us see. Definitely, if it is not possible, then you do it. Huh.
Okay, sir.
But the major problem issue is that you will face several difficulties. Huh. And there you try to see that what are those things. But
Okay.
important thing is that you have done it. That is important. Now, Gaurang, you wanted to say something?
Yes, sir.
Gaurang Mohta?
Yes, sir.
Hmm.
Sir, I wanted to ask how is this lab conducted in offline mode? I was just curious on how designs are made.
I'm not very clear. What is your question?
Sir, how is this lab conducted in offline semester? Do we implement all the designs in real life?
No, it is very difficult. We try to implement one or two, but it's very difficult because I will have to give this working space also to the students so that they should come into the lab. That should be the ideal condition situation. But we will have to work in the lab, and you will have a free space, free time, and these things also. Lab should be free. That is the problem. We cannot really afford to do that one. But some part of this one, we often say that you try it and see it, like this thing. So it is not much difference from the other year's design. Okay. Any other thing? Any other question? So I will just take a.
Sir,
Yes.
sir, is it necessary to put the cost estimate for every experiment? Exact cost?
I know it is not easy to get this one, but definitely in the actual practice, whenever you put the design and like this, they will look for what is the production cost on that. And definitely it is not also complete only the component cost, but the manpower cost is also important, and that estimation is done. So that part you may skip it.
Okay, sir.
So I will just take attendance, and then Rishi Prashant.